Gary Madaras, you're the acoustic specialist with Rockfon, based out of Illinois.
Right, in the Chicago area. Nice to meet you too, Dean. Yes.
Near Midway Airport.
Pretty close. Yeah, that's where Rockfon's headquartered.
It's been there for quite a few years too, hasn't it?
Well, Rockfon's a Danish company that acquired Chicago Metallic, right? Chicago Metallic was a grid and metal ceilings company, over 100 years old in the Chicago area. And when Rockfon decided to come to North America, they acquired Chicago Metallic, and that was in the 2013, 2014 timeframe.
Oh, great. Right. I remember Chicago Metallic. That makes
A lot of people do. Good brand.
Yeah, very solid. Well, Rockfon's a great brand too. It's
Great.
really established itself very, very well in the US already.
Thank you.
So acoustics. So I'd love to hear about your time at University of Florida where you became a PhD in acoustics.
Yeah.
Could you tell us a little bit about it?
Sure. It's excuse me, it's odd. You go around and you ask people what they do, start a conversation. And when I say I'm an acoustician, they have no idea what that is. And I talk about, well, I control noise in buildings. And there was this sort of surprise, like I had no idea, anybody did that. I said, oh, sure, there's scientists that do it. There's proven products. There's a whole profession and industry behind it. And so awareness is a big thing. But at the University of Florida, there was a focus on sort of that top level acoustics, particularly performing arts and cultural centers. So my dissertation work there, I was building 1 to 10 scale models of music performance facilities and doing testing inside, crawling inside, and using automotive creepers underneath, and taking out little scale mannequins and theater seats and putting the microphones in. And excuse me, we have at that time a spark, an electronic spark as the sound source. So this big electronic wand would come in the stage, and we'd fire it off, and you'd see this spark, and miniature microphones would record the sound. But there's only one acoustic metric out there that considers sound at both ears, because we have 2 ears and our brain fuses the sound together. So my research really focused on that one parameter called intraoral cross correlation, right? Intraoral, 2 ears, and cross correlation is just a statistical comparison, which makes it between 0 and 1. But anyway, you wanted to drive that number down, but we didn't really understand how to do that architecturally. So in my model, I would put balconies in and see if that affected this number. Or I'd put an overstage reflector in, or I'd put absorption on the back wall or the side walls. And through that work, we really gained an understanding of how this parameter can be actually controlled and decreased in real buildings.
Oh, fascinating.
Yeah,
it must have been really cool to work on. That sounds like a good PhD, like fun.
Yeah, it was. It's very physical, right? Because right now it would all be digital, because we've, to a large extent, moved away from that physical scale modeling. There's some great acoustic analysis softwares out there based on 3D computer models. So then I'd be spending the whole time in front of a screen, instead of that physical stuff, which I enjoy more.
There's a new performing arts center that's opening up in North Carolina, and we just did a project tour with them. And so it's at the point where they can actually change the acoustics to match other theaters.
Oh, great. Is that physical or electronic, though?
Electronically.
Okay.
And it was quite fascinating. We as a consumer take it for granted. Like, we complain when acoustics are bad, but we never Gary, thanks for making this room sound good.
Right. It's one of those professions where if you do it right, no one should notice, or maybe in performing arts world, but typically people don't go in and say, wow, this school really sounds good, or this library really sounds good. They expect it to sound good, and they only notice when it doesn't.
It seems like the last few years, acoustics and the discussion of acoustics is really cranked up. People are really talking more and being more sensitive to sound in environments.
Absolutely. And that's reflected in the codes and standards and guidelines. A couple years ago, you didn't have the well building standard with a sound control section. And For example, LEED addressed healthcare and schools, but not other types of facilities like offices. So much greater awareness. Unfortunately, it's a bottom-up movement. It's greater expectations from building occupants, school districts, municipalities, as opposed to, sort of top-down governmental regulation, like this vacuum cleaner shall not be, greater than 70 dBA. And in some countries that it works that way, top down.
Well, let's, for now, talk about speech intelligibility.
Okay.
And now, I could be totally off on this, but I read that some rooms you want to put more focus on speech, and other rooms you don't. Why is that?
Well, you have to think fundamentally, why are people together? If people come together, a classroom is a great example. They're coming together to communicate and learn. A large portion of that is verbal. So speech intelligibility is very important. High speech intelligibility is very important. A lecture hall is another good example. A church or synagogue where we're communicating about religion. Speech intelligibility is all very important. So that's one category or one bucket of rooms that need to be designed a certain way. But people are not always together for that reason. Sometimes they're forced, together closely for other reasons. They don't necessarily need to be in an open office is a good example, but a even better example is a patient ward in a hospital. You walk down, particularly in an older hospital, the corridors are packed. There's, probably at least 2, if not more, patients in each room. The nurses' station is packed, and they're not all together to communicate with each other. In fact, a patient who's trying to recover needs deep sleep. And if, we're tuned to listen to conversations, particularly when we're ill, right? And in the hospital, we want to know, are they talking about me? Am I on the uphill or the downhill side of this? But we can't easily tune out speech when we hear it. So when a patient hears the nurses talking about their weekend or what they're going to do for lunch, and we all do that at work. It's not not that they shouldn't do that. It can disturb sleep. It can impede recovery, and they've actually seen 30-day readmission rates increase when people don't get enough sleep in the hospital, meaning that there's complications. They're not recovering. So there's those 2 buckets, and I think it's important for architects, designers, specifiers to think, what am I actually trying to do acoustically in this particular building or space? Am I trying to allow people to communicate? Is speech intelligibility a good thing, or is it a bad thing? Could it actually deter from good use of the space I'm designing?
No, it makes total sense. Let's go back to the office space part, if we could, for a moment.
Sure.
Right. So the open plans, open access, but still, I need to control my own thoughts.
Sure.
So that's I'm just throwing this out. That's as complex as a church needing to communicate to all the congregants.
In some ways, it's even more complex. You would think that because in a church or any type of religious facility, there's a limited number of sources. They're there together to communicate. People want to hear what's going on. The slight complication or complexity with religious facilities is, is it what's the range of things going on? Is it, organ all the way down to natural speech, which is a huge range. We're talking about acoustic variability. But in an open office, you're trying to put many people together. And what's happened over the decades, even in the 80s, there was these cubicle farms and everything was sound absorptive, and we've really strayed from that. There are some very well-known and proven rules to acoustics design to make open offices work well. People don't want that anymore. They don't like that aesthetic. We've moved to really open spaces. Partly due to the sustainability and green movement, we've moved away from some materials, for example, carpeting, and that leads to more reflection, more noise. You take the cubicles away and you lose that occupant density control. And what we see now, people sitting elbow to elbow, face to face around tables, and it's just very difficult to, speech privacy isn't really expected anymore. We talk more about what's called distraction distance, and trying to minimize how much sound travels and distracts so many people in that radius.
Oh, that's fascinating.
Yeah.
A friend of mine works at a LEED platinum building, and it's all open. And he said everybody tries to get there about 6:30 in the morning so they can get the conference rooms before everybody else shows up.
Right.
Just so they can have like that. But my assumption is that by involving you in that planning, that's not going to happen. You're going to figure out how to make it a more livable space.
Right. That's part of my role at Rockfon, right? And like I said, there's a science to this. There's industry professionals called acoustic consultants. And there's the National Council of Acoustic Consultants, ncac.com. Anybody can go there, look for acoustic consultants in their area or elsewhere, and bring that professional on board. But yeah, it's surprising how many problems are realized only after occupancy and are dealt with at too late of a date. Then it interferes. It's more expensive. It interferes with production or occupation, whatever.
I was just at a building some years ago, and we were walking through, and the architect said it was perfect until the people showed up.
Right. Right. Actually, a lot of it's funny because a lot of the acoustic measurements that we as acousticians use and judge are for empty buildings. We go in to measure the noise level of the mechanical systems and electrical systems, but that doesn't include occupants, right? And we judge, is it successful? Did we meet 35 or 30 or whatever the number is? And then the people come in and it's 80. So it's like, well, does it really matter if it's 30 or 35 without people when it's 80 when everybody's in there? Yeah.
So can we just get clarity? Let's build a room together for a minute, and what goes in? I don't know what, like healthcare, and your example is really profound. Should we talk about that on like in an emergency room type environment or intensive care unit? What kind of decisions have to be made to ensure good health?
Well, that would be a situation where, and when I say it's not a speech intelligibility room, we're not talking about a doctor and a nurse and a patient that are all standing within arm's length from one another and talking, right? Yes, they need to understand each other, but overall that room wouldn't be categorized as a speech intelligibility room. You don't have 30 students, you don't have 100 worshipers or more, right?
Oh, okay. Yeah.
Or 1,000 people going to a theater. Pretty much when people, a small group, 1, 2, 3, 4, are arm's length away from one another, the room doesn't contribute a lot because they're so close, and that the loudness of the direct sound from the mouth to the ears is so loud. So in that healthcare environment, you mentioned, for example, an emergency department, maybe waiting room, triage, so forth. So you've got very high noise levels. You could have multiple people talking, kids playing or crying, people in distress, ambulances coming in, pages over. So it's a very loud, noisy environment. And also those conversations that are happening maybe between the admittance nurse and the patient needs some amount of privacy. So it's a very complex situation. And in those type rooms, really the more distance you can provide and the more sound absorption you can provide. And by sound absorption, a room surface, a ceiling, a wall, a floor can be multiple different materials. We go into rooms and buildings and we see wood and we see metal and we see glass and we see fabric and upholstery, and right, there's a lot of options. And some of those either very sound absorptive, they're porous, and the sound energy can get into the material and get dissipated, by converting to heat. Or it can be very non-porous, like metal and glass and polished stone, and that sound can't get in there and it reflects off. And the more of the latter, that stone, that metal, that glass, in the room, it becomes very reverberant, very loud because the energy is contained. So in those type rooms, we're talking about an emergency department in a hospital. In similar places, you want more of the former, the very absorptive, porous, soft materials, and to absorb that noise. So the ceiling is actually probably the key to that equation, because you can think, well, I'm in a hospital emergency room. Do I really want soft, fuzzy stuff on the floor and the walls, right? There's maybe some infection prevention issues, some high maintenance and cleanability issues, but that ceiling is up out of harm's way for the most part. And it's really the biggest exposed surface in the room. So that's why we'll see the acoustic treatment very frequently overhead on the ceiling. And there's again, even if you think, okay, I want absorption, I want the ceiling, you can have a perforated wood with sound absorption behind it, or metal, but by far the biggest option are the acoustic ceiling tiles. A lot of people that are in their office or some other commercial facility could probably look up now and see sort of white or rectangular squares in a metal grid, and that's what I mean by acoustic ceiling tiles. Yeah.
Oh, so, okay, it's complicated. So if I'm an architectural firm, will I have on staff a PhD of acoustics, or is it that I'm going to work with the building product manufacturer that has that expertise, and that's my expectation that, okay, I'm going to choose Rockfon and I'm going to get these services?
It works in a multiple different ways, right? There's a small percentage of AE, architectural engineering firms, that are bringing specialists like acousticians on staff. And I could rattle off a handful of them now. More often, the architect doesn't employ those specialists directly 100% of the time. They go out and they hire the consultant. Some manufacturers are very knowledgeable. They have their PhD acousticians or other acousticians. You don't have necessarily. My PhD just means that I didn't want to enter the workforce right away, and I wanted to stay in Florida. It just ended up that after a certain amount of time they gave me the degree. But yeah, they're manufacturers should be able to say, this is our product. This is the best product for your application. Here's how you use it. Here's how much you should use and how to install it. And for example, we do that with our products, but there's so much more to acoustics. There's environmental noise. There's building system, HVAC, mechanical, plumbing noise, right? And we don't go into that because we don't cover those products. So yeah, there's options, right? And employ someone in staff, hire a consultant, or go directly to a manufacturer for the application of their products.
Okay, before we finish this one podcast, the can we go through some of the technical like terms like signal to noise ratio? What does that mean? And signal and stuff like that.
Yeah, so that's sounds real technical, but it's very common sense. So we were talking about speech intelligibility rooms. In a speech intelligibility room, you want the signal, which is what you want to hear. It could be a musician playing a violin. It could be a teacher talking. That's the signal. You want that to be very loud, very high. Noise is anything that would prevent you from hearing it. It could be an airplane passover. It could be reverberation in the room. It could be the mechanical system kicked on and you hear the fan. All of those things make it harder to hear the signal. So you're trying to say, to increase the signal to noise ratio. A high signal to noise ratio equates to speech intelligibility. So the signal side of it, you think, well, that's someone talking, that's completely out of the designer's control. How fast they talk and how loudly they talk, and do they have an accent or not? That's all out of the designer's control. And I agree, and that's all very important. But if you place a very good speaker in a room that is too reverberant, still, no matter what they do, no one is going to understand them. So part of that signal is in control of the designer. And give a couple quick examples. In a concert hall, we were talking about concert halls, you'll often see a very big reflector over the orchestra, right? And that is to take all the sound that comes up and redirect it to the audience. So that's considered part of the signal, not only the sound coming from the orchestra, but what's very quickly reflecting off that reflector. Maybe a little more everyday, same, they do that in churches too. And sometimes you can do that in classrooms. So reflective surfaces, right? We were talking about stone and metal and glass and concrete. If those are used in the right places, the sound that's coming from the speaker or the musician reflects off those to whoever's trying to listen and increases that signal. But not every surface will do that. The noise side of it is much more in the designer's control. And when I say noise, a lot of people think about, the kid walking down the corridor that's talking, or the fan, the exhaust fan that's above the ceiling, or whatever. But actually the worst kind of noise is actually reverberation in the room. We talked about all those hard surfaces, sound bouncing around. And the reason I say it's the worst is because it's always present for every word, because the kid walking down the corridor talking and you hear it in the classroom, how often does that happen? How much speeches are they actually interfering with? But that reverberation is always in the room, even if the rest of the building is empty and there's one class going on. And that's why I think it's the worst. And again, that leads us back to the absorption and particularly ceiling absorption. But yeah, that signal to noise ratio, high signal to noise ratio, speech intelligibility. Low signal to noise ratio, it's very hard to understand. It can be loud. A lot of people say, I can't hear. They can hear, it's plenty loud, but it's so muddied because that signal to noise ratio is off that they can't understand.
Right. Thank you for doing this podcast with me.
You're welcome. It was fun. Hope we can do another one.
Yeah, great.